we want to find the integral from negative infinity to positive infinity of e to the negative x squared dx. Now, a few things pop out to us. First off, this isn't multivariable at all. It's a single variable, x. Why are we bringing it up now? Well, that's a great question. Another thing you might say is, you've been telling us time and time again, you can't integrate this, you can't integrate this, and now all of a sudden you're telling us, well, let's integrate it. Now, let's clarify that point. When we talk about you can't integrate, what we really were saying is there's no nice antiderivative. So e to the negative x squared does not have a nice antiderivative, and we're not going to find one. So if you expect us to find one, well, that's not today. Now, you might say, well, then that means you can't integrate, because you have to have antiderivatives to integrate, and the answer is no. Integration existed long before differentiation. There were a couple thousand years in human history where people were talking about the ideas of integration before they started talking about the ideas of differentiation. So just because we don't have antiderivatives does not mean we can't integrate. All right, well, so how are we going to find this? So here's the idea. There's a couple of sort of like, that doesn't make any sense about why you would do that, but okay, kind of moments that are about to happen. So the first thing we're going to do is say, well, let's say this is our integral we're going to find. We're going to call it L. And along the way, we're going to say, we're not going to find L. We're going to start by finding L squared. So in other words, two copies. Negative infinity to infinity, e to the negative x squared dx. And then I'm going to have integral negative infinity to infinity of e to the negative x squared dx. Now, so far that's absolutely correct, and somehow it seems not very useful. But here's a few things we can do. Now, notice that we're doing a definite integral, and we're integrating with respect to x in both times. But in some sense, x is what I like to think of as a dummy variable. And it goes away. So after you integrate, there's no more x dependence after you do your integration and your evaluation. So here's what we're going to say is, let's actually make this second integral, and instead of calling our variable x, let's just change it to y. Now, it doesn't change the answer because it goes away. So regardless of what variable name we call it, we'd still get the same value. So now I have two integrals. One of them is an integral of x. One of them is an integral of y. Now at this state, you might say, okay, well, how do we turn it into a multivariable integral? Because that's our subject we've been talking about. And now we use an idea, sort of the opposite of what we did a few lectures ago. So a few lectures ago, we had this idea of saying, look, we can sometimes pull integrals apart and do them separately, but we can do the opposite. Suppose we have two separate integrals. We can smush them together. And that's what we're going to do. So now that we have different variable names, smushing our two integrals together, we get a single integral, negative infinity to infinity, integral negative infinity to infinity, of e to the negative x squared, e to the negative y squared, dx, dy. So now we're like, aha, multivariable integrals. That's why we're talking about it. But still, how do we make progress? One thing you might notice is that we can rewrite e to the negative x squared times e to the negative y squared. That becomes e to the negative of x squared plus y squared. All right. Well, at this point, something should be like, whoa, I remember x squared plus y squared. When I see stuff like that, what do we think? Polar. Polar, because x squared plus y squared becomes r squared. So let's think about this. We're going to now, big idea is to switch to polar. Now, when we're switching to polar, remember, every integral always has three components. And this is going to become really important when we get into, about a week from now, the this idea of changing coordinate systems. So it's important to remember we always have three components. One component is the region we're integrating over. Another component is the function. And the last component is how we break things up. So this dx dy, that's how we're breaking things up. That's acting like our dA. In polar, what does dA become? Yeah, r dr d theta. R dr d theta. Now, e to the minus x squared plus y squared, that's easy. That's e to the minus r squared. Let's talk about our region. Now, currently, we're having x go from negative infinity to infinity, and y go from negative infinity to infinity, which means we have a lot of stuff we're integrating. We're integrating over everything. So, how do you represent integrating over everything in terms of polar? Where will theta go between? 0 to 2 pi. Okay, so let's work on writing up our new integral. So, we're going to have e to the minus r squared, so our new function. R dr d theta, that's how we're breaking things up. Theta goes 0 to 2 pi. What about r? Where does r go between? Yeah, it's 0 to infinity, 0. Now, why 0? Well, because we always think about coming from the center. So emanating from, if you like, that pole at the origin. So the theta says, how much do you turn? And the r says, how far do you go out? Well, I only have to go positive, starting from 0 and heading out. Now, we're in luck. We have an r there. Okay, well, to make ourselves even more lucky, we can put a 2 and throw in a half somewhere down there. All right. So, can we integrate e to the minus r squared times 2r dr? And we're integrating with respect to r. Do you know that? Now you can do u substitution. If you do u substitution on the side, you could say, well, let u equal negative r squared. Du is minus 2r dr. Whoops, I forgot the minus. I'll put it on the other side. Minus du is 2r dr. So this becomes, in the end, it becomes e to the u du with the minus. So it's minus e to the u. So in our case, it would be minus e to the minus r squared, evaluated from r equals 0 to r equals infinity. Now, we have to be a little bit careful. This is, technically, it's an improper integral because there's an infinity involved. But it's a nice kind of improper integral where it's like, we understand what's happening. So we can evaluate. Now, when we say the words evaluate, we're really saying evaluate, because infinity isn't something you can plug in. But it is something you can say, what happens as I go towards? So, as r goes towards infinity, what happens to that value of e to the negative r squared? It goes to 0. Now, at r equals 0, I don't have to go towards it. I can actually just plug it in. What happens to e to the negative r squared? It goes to 1, because it's e to the 0. So, when I evaluate, this becomes 1. So what do I have? Well, this becomes 1/2 integral 0 to 2 pi d theta. And that's an easy integral. In fact, that one is one you can probably do in your head. 2 pi, then there's the half. So you get pi. Now, is this the answer? Well, let's follow it back. We're going along the equal signs, and we see, it's not L, but it's close. L squared. So, what is L? Well, it's the square root of that. And now you might say, well, plus or minus? No, we just want the plus. Because this integral is integrating a function which is always greater than or equal to 0. And so our conclusion is that L is the square root of pi. And that's it. There's the answer. Now, for those of you who have ever had statistics, you might say, so that's why there's a square root of pi in all these formulas for statistics. Because one of the things you may have heard of, there's something called the bell curve. It might be the most famous, the curve, that you know of. And the idea is that in statistics, if you have enough random things happening, it tends to look like a particular shape. It tends to look a shape that behaves something like this. That's a terrible drawing. But if it wasn't a terrible drawing, you would say, hey, I recognize that. It's really behaving something like e to the minus x squared. And so in statistics, they needed to know this function. And in particular, they said, well, what's the total amount of area underneath the whole thing? So you can make sure that there's the amount of area is 1. Well, we know how to answer that question now. There we go. There we go. All right. A little bit of unexpected multivariable calculus application, and a nice showing you that, hey, sometimes polar is good. There's another punchline here that says, you know, in mathematics, pi shows up quite a lot more than you'd expect. Because when you look at this, initially, there's nothing to do with pi there, but sometimes the shortest distance between 2 points is to go on a circle through what's called the complex plane. That's a different kind of a story. All right, now on to today's real topic. We're talking about integration, which really just means let's find the totals. And where are we at? Well, previously, before our class, we learned about how to find integration over intervals. So that's the first one we did. And we did this calculus 1. So suppose I have an interval. I'm going between 2 points, say A and B. I know how to find the total. Now you might say, total what? Well, that's a good question. For now, let's not worry too much about that detail, but if you want to have something to help you think about it, an example to think about is mass, because that's something that's intuitive that will work as we get up to bigger shapes. Maybe you can think of this as a wire, and the wire has varying amounts of density. You want to say, what's the weight? That's something we actually talked about last semester in Calculus 2. All right, so we're getting closer to Calculus 3. All right. Well, now, what we talked about in the last few sessions said, what if our region is two-dimensional? So here I have a region, two-dimensional, in the plane, and I want to say, what's the total over my region R? We said, all right, we have a way to do that. We can set up what we call a double integral. And the double integral is somewhat reflective of the dimension of what we're integrating over. So here, it's a two-dimensional object, so it's a double integral. And we're going to integrate f of xy dA. And the philosophy was, let's take what we're trying to find and break into little tiny pieces. Now, the reason we break things into pieces is what often happens is that f of xy, it can change a lot in the big. So in other words, if I step back and look at it, I can see all sorts of behavior. It might be going up and down a lot, and but in the small, when you look over a little tiny piece, it's not changing very much. So that's why we like to think of things of breaking things up. So now we're to today. We say, well, look, what if I have a three-dimensional object? So now my thing I'm integrating over, I'll call it a solid. So I have some solid shape, and I want to find the total. Well, it's a three-dimensional object, and so we do a triple integral. So then again, the number of integral signs involved has something to do with the dimension of what we're considering. So if we're going over a three-dimensional region, it's going to be 3 integral signs. So the integral over our solid f of xyz dv. So the dv, the intuition is we're breaking things up into little tiny chunks. Now our solid, when we break it up as little tiny pieces of volume. And asking what happens on each little piece and add it up. Okay, so that's the idea. Now, where's the basic theory? When we're thinking about how to set things up, our basic philosophy is to say, hey, I'm going to take this big thing, and what I'm going to do is I'm going to chop it into little tiny cubes. And so I have my solid, and here's one little tiny cube. It's blown up over here. And I say, okay, let's understand what's happening on that one little tiny cube. Now, you'll notice that my little tiny cube it's very easy to understand it because cubes are flat. And we understand flat things really well. So I say, look, there's a little change in the y direction, there's a little change in the x direction, there's a little change in the z direction. So I can say that the amount of volume of that little cube is delta x, delta y, delta z. All right, so I can find the volume of that part, and I can ask how much does it contribute? Well, the answer is it's the value of the function on some point in the cube. And the point here is that the value of the function is about the same, no matter where in the cube I look. So if I want to find the total, what do I do? Well, I sum over all I, some j, some k. So I'm thinking of I as I'm chopping in the x direction, j I'm chopping in the y direction, k I'm chopping in the z direction. And so really, this is, for each piece on the inside is one cube. The delta v, that's the size of the cube, and then the value of the function on there. And, of course, smaller and smaller chopping, better and better estimate, it becomes the integral. I really should have said here that when I talk about the total here, this is really approximation right there. And what happens is in the limit, it becomes exact. Now that's the idea. What's the practice? How do we actually do it? Well, not surprising, we're going to sort of generalize what we were thinking about for two-dimensional integrals. So in two-dimensional integrals, what did we do is we said, instead of cutting things up into little tiny squares, we're going to take strips, very thin strips, and see what happens. Now for 3 dimensions, we're going to do the same thing. We're going to take slices. So I have my solid, and I take a slice. And once I've taken that slice, what happens? Well, this slice looks like a two-dimensional object. So as I pull the slice out and lay it down. So I can now look at this slice. This is at a fixed height of z. And I can ask, what is this behaving like? Well, what I can do is now I can come here and I can start thinking about what I did before. Is I can find a way to slice that as well. So if I want to find the total, which is this integral, what I can do is I say I'm going to add up all the slices. What's the contribution from a particular slice? Now the slice depends on where I slice, because depending upon where I slice, I might get a lot or I might get a little. It just depends. So there's the total times the little bit of dz added up. How do you find that total from that slice? Well, now you're back into a two-dimensional integral, and now you do what we did before. So, how do we actually do these integrals? The answer is, we do them by doing iteration. Iterated integrals. But now, instead of 2 layers, we have 3. Our onion has grown. It's another layer. And I'll tell you, that layer is going to cause a lot of tears. So get ready for it. Now, I want to talk a little bit about sort of what to look for and what to understand. Notice I've put stars on this part down here, just because those are the bounds. And the bounds, of course, depend on the problem. But I want to be really explicit here, because it's helpful to understand what the bounds should be. Because if you can understand what the bounds are, it makes it more likely you'll get the bounds correct. So a couple of notes here. I want to have this picture still visible for a second. Is that when you're setting up the bounds, the outer bounds, and when I talk about the outer bounds, I'm talking about the outside layer. So the outer bounds always go between 2 numbers. So the outermost thing is always between 2 numbers. The next level in, so now I'm talking about these middle bounds. So that would be what would go with the y here. So the next level in, I'm going between 2 curves. And if I keep pushing in a little bit further, so now I'm into the inner bounds. Here, what would be the x, that's between 2 surfaces. So when you're thinking about setting up an integral, or you're trying to understand what an integral is, it's useful to remember what corresponds to what. The outside corresponds to numbers. Next layer in corresponds to curves. The last layer corresponds to surfaces. You might say, well, what if we ever did a 4-dimensional integral? Well, two things. We won't. But if we did, we would call it a hypersurface. That's just a cheap way of saying we ran out of names, so we just add the word hyper in front of everything. This is kind of like what they do for quantum nowadays. Well, if we just throw the word quantum in there, then we can say anything we want in a movie, and they'll just buy it. All right. Now, there's another thing to say. Last time, or maybe it wasn't last time, but in the last few times, we've talked about this idea of we can change the order of integration. And we can say, oh, you could integrate dx dy, or you can do dy dx. There's two ways to go. But now that we have 3 dimensions, now we get a lot more ways we can go. There are 6 possible ways that we can order our integrals. So there they are. Dx dy dz, dx dz dy, so forth and so on. You'll notice that one of them has been marked in a slightly different way. This one in the very bottom right corner. It has a box around it, as if to signify this is special. Now, it is not special in that it gives the right answers and the others give a wrong answer, but it is special in the following sense, is that you have been trained to think in that way. And what do I mean by that? I mean, you have been trained to think of x as numbers, y is a function of x being curves, and z is a function of x and y being surfaces. So this is the one that's going to be the most easy for you in terms of how you've learned to think of things. Now, it may or may not be the right thing to do. Oftentimes we will sort of nudge you one way or another. But if it's not giving you any other information and just says find it, I would strongly encourage you to start with this order, dz, dy, dx, because again, it is the way that you have most often worked with things. Okay. All right. So now, examples, and I am predicting we will probably get to spill over into our next lecture because there's so many wonderful examples. Let's start with something very easy. Find the integral over a solid of the function x squared yz dv. And S is the solid where x goes from 0 to 2, y goes from 0 to 2, and z goes from 0 to 1. Now, if you draw this solid, it's not very hard. What is it? Do you recognize the shape? Yeah, it's a box. X goes from 0 to 2, y goes from 0 to 2, and z only goes up to 1. So it looks something like that. Now, boxes are very nice things to work with. In fact, they're kind of our friends because they are flat. We like flat things. Flat things are very useful and convenient. So, which order would you like us to set it up in? There's lots of orders to pick from. There's not a wrong order. In case you're like, oh my gosh, I don't want to say anything because I could get the answer wrong. See, this is like one of those rare times. It doesn't matter what you say, you're going to get it right. And I can feel someone says, oh, already theta. That's wrong. Okay. But okay, all right. Well, okay. Since you're not picking, I'll pick. All right. All right. Suppose dx dz dy. So I want to find this integral, x squared yz. And I say, look, I actually want to find it. And so if I want to find something, the way we find things is iterated integrals, dx dz dy. And when we're doing these types of integrals here, the safest thing for us to do, the easiest thing for us to do is just sort of say, okay, let's think about what's happening for y. Well, where does y go from? 0 to 2. Okay, so now I've fixed y. Well, it doesn't really matter which y we pick, so maybe I pick this value of y. And now that I picked a value of y, I see that when I look in that slice, I see a rectangle. Okay, it's a rectangle. Well, where does z go from in that rectangle? 0 to 1. Okay, so now what I've done is I've sliced the rectangle, and then I say, okay, so there's the slice of the rectangle. So see, this is like the second level slice. And now it's a slice just where x is varying. Y and z is fixed, but x is varying. And where does x go from? 0 to 2. See, the nice thing is the reason that rectangles are so nice, particularly in Cartesian coordinates, not so much in other coordinate systems, but in Cartesian coordinates, it has such a simple description. Now, there's not a lot of space left, so we're going to do the rest of this problem by just making a quick observation. Remember how we said we can pull integrals apart? We can still do that with triple integrals, as long as the bounds are constants. So if your bounds are constants and your functions allow you to pull things apart, in other words, it's a function of x times a function of y times a function of z, or whatever variable names you're working with at that time, you can pull it apart. So this is something we did earlier. So what does this become? It's the same as I'm pulling off the part that has to do with x. Well, that would be 0 to 2 of x squared. Pull off the part that has to do with y, 0 to 2 of y. And pull off the part that has to do with z, and that's 0 to 1 of z dz. Again, I can only do this because it's a box. And my function has a nice form where I can separate it, pull it apart. Not everything has that form, but this does. All right, well, integral of x squared, that's 1/3 x cubed. I'm going to evaluate that from 0 to 2. Integral of y, that's a half y squared. Evaluate that from 0 to 2. Integral of z is a half z squared. Evaluate that from 0 to 1. And I'll end up with getting 8/3 from the first term, 2 from the second, and a half from the third, which means when I put them all together, that my answer will be 8/3. Okay, so that was a fairly straightforward, because we had a box. All right, not everything has to be a box. So here's an example. Find the integral from -2 to 5, integral 0 to 3x, integral y to x plus 2 of 4 dz dy dx. This is not a box, and very unbox-like, but that's all right. Not everything has to be nice. We have to save some things for the test. But again, this is maybe a time to remind ourselves what's happening. So the outside integral is going to go with the outside d term. So that's the -2 to 5 is hooked up to the x. So it's going from the integral x equals -2 to x equals 5. Then the next layer, that's associated with the next term, y. So it's y equals 0 to y equals 3x. And now we're seeing, oh yeah, that's like a curve in the xy plane, because I'll be in the xy plane when I look at the last two. And then the next layer in, that's associated with the z. Z equals y to z equals x plus 2. And if I think about what's going on here, I say, okay, that makes sense, because these are surfaces, like z equals x plus 2 and z equals y. Those are actually nice surfaces. They're planes. And I should be in a surface in a three-dimensional space, namely in the xyz space. All right, well, how do we do it? Well, these are our onion problems, one layer at a time. And you work from the inside out. So my inside is the integral with respect to z. What's the integral of 4 with respect to z? 4z, yeah. All right, so we come integral -2 to 5, integral 0 to 3x. I'm going to suppress the notation. I just wrote it down to remind ourselves whenever we see something, we understand that notation means something. So it's important to know what things mean. So 4z evaluated from z equals y to z equals x plus 2 dy dx. So we plug that in. That's integral -2 to 5, integral 0 to 3x. Now I'm going to get 4x plus 8 minus 4y, and that's integrated dy dx. All right, what's the next layer? What do I integrate next? Integrate with respect to y or with respect to x? Well, the reason why I'm asking, no. Okay, now with dy, because we're working from the inside out. All right, so now what's the integral of 4x plus 8 minus 4y with respect to y? The outside still is waiting for us. So integral of 4x with respect to y, 4xy. Integral of 8 with respect to y, 8y. Minus 4y with respect to y, minus 2y squared. And we're going to evaluate from y equals 0 to y equals 3x. And then once we've evaluated, we're going to integrate that with respect to x. Well, the nice thing is 0 is convenient. That makes everything 0. So when we plug in 3x, what do we get? Well, negative 2 to 5. 4x times 3x will be 12x squared plus 8 times 3x, which will give us 24x, minus 2 times the quantity 3x squared. Well, that would be minus 2 times 9x squared, which will become minus 18x squared. And we're doing that dx. Well, negative 2 to 5, 24x minus 6x squared. We might as well put the x squareds together. Hopefully that saves us some time. And now we're like, great. This is wonderful. We're in Calc 1 territory. We know how to do these. Integral of 24x with respect to x. 12x squared. Integral of 6x squared with respect to x. Well, something x cubed. What goes in front? Yeah, it's 2. And evaluate from negative 2 to 5, which is something. Well, okay. We've come this way. Let's finish it. All right. 12 times 25 is 300. Very good. 5 cubed is 125 times 2 makes 250. So 300 minus 250. Subtract. 12 times 4 is 48. And then we're going to have minus 2 times minus 2 cubed, which will end up becoming plus 16. And 48 plus 16 turns out to be 64. So I have 300, subtract 250, subtract 64, giving us a final answer of negative 14. Now, should we be worried that we got negative 14? Not yet. All we know is we were giving an integral. Integrals are allowed to be negative because integrals represent totals, and some totals have signs. So, as a common example, bank accounts. It's possible to have negative values in your bank account, something that students know very well. So it's possible to be negative. Totals can be negative. Now, if you were doing a problem and you were saying, hold on, this is supposed to represent something which is positive, and you got a negative answer, you should be like, let me double check my work. But as for right now, it's okay. All right, well, so we can do these triple integrals. It's just a matter of being patient. So what's there left for us to learn? We know how to do them. We do them one layer at a time. What's left for us to learn is how do we change that order? So maybe we're given an order that's not very useful. And we want to change the order of integration. And not just change the order of integration. This is also related to the idea of setting up. So this is all tied together. So if you don't like the idea of like changing the order, maybe setting up is also just as appropriate. Setting up kicks in about step 2. So a lot of this should sound very familiar because it's basically the same process. Now, what's the process? First off, identify what the bounds are. So if you're given a triple integral, where do we find the bounds? Well, when we're given a triple integral, the bounds are here in these integrals. So, for example, x equals negative 2 to 5. Y goes from 0 to 3x. So 0 less than or equal to y less than or equal to 3x. Y to x plus 2 says y is less than or equal to z is less than or equal to x plus 2. These are where you're getting your information about your bounds. Or it might be saying, hey, here I have some various surfaces and I want to set up an integral which is between a collection of surfaces. That's where you get your bounds. Then the next step is try to draw a picture. Now, unfortunately, this is a case where you want to try to be reasonable. You don't have to be precise, but just drawing wiggly lines might lead you astray. So the good news is, we'll tend to give you things which are very simple to draw. The bad news is that doesn't mean it's trivial, but at least we'll be able to draw it. And when in doubt, just try to be simple. Say, okay, do I understand what's happening in the xy plane? Do I understand what's happening in the yz plane or the xz plane? Oftentimes, if you can understand what's happening in those planes, then it's not so bad to piece it together, which is what is meant here by this comment, work up one dimension at a time. Now the next step is to label the bounding surfaces. So this was the same idea as before. Maybe we said, okay, I'm in the xy plane and I have this curve, I don't know, say y equals e to the x. Well, I could also write it as x equals e to the y. So when we need to, we want to say, okay, instead of writing this as a surface z equals some function of x and y, maybe I should write it as x equals some function of y and z. So to talk about label is also talking about relabel. How do I change it so that I have it in terms of the right variable? And oftentimes, it's not obvious which is the right variable to do. So step 3 is a little bit fuzzy on when it happens because step 3 and 4 sort of come together. And now, step 4, set up the bounds. I like to work from the outside in. And I say, okay, what's my outer variable? Well, what does that variable go between? It goes between two numbers. Great. Now let's go to the next variable. Where does that go between? It goes between two curves. What are the right two curves? And so forth and so on. And there's a tip here on the bottom. If you want to simplify the process, in particular in the last step, step 4, look straight down an axis. And you'll be able to reduce the dimension. It simplifies the problem. We'll talk about what that means as we go through and do some examples. And hopefully, we have enough time to get through 2 examples, if we're lucky. Although I have about 4, so we have time next time. Next time, we'll get to practice more. So here we go. Example. Change the order of integration for the integral from 0 to 4, integral 0 to 2 minus a half z, integral 0 to 1 minus a half y minus a fourth z, f of x, y, z, dx, dy, dz, and we're going to change the order of integration to be dz, dy, dx. All right. Well, let's begin. First thing we want to do is probably following this plan, is figure out the current bounds. So, what does this outer integral tell me? I'm going for z goes between 0 and 4. Okay, so z is between 0 and 4. And in some sense, that's not too hard for me to imagine. That says I'm just in the z direction, I go between 0 and 4. There's not much left to the imagination. Let's talk about my next layer. What's true about my next layer? What does that say? Y goes from 0 to 2 minus a half z. All right. Now let's pause for a second. Let's think about what's happening here. I have the variables y and z, which means I'm in the yz plane. So I'm going to draw the yz plane. So here we go. Here's the yz plane. I know z goes from 0 to 4. So this is z going from 0 to 4. And then y is going to go from y equals 0, which is actually this line segment right here. on the z-axis to the curve y equals 2 minus a half z. Well, what does that look like? Well, when z equals 0, I'm going to be at 2, because 2 minus 0 is 2. When z equals 4, where will I be? I'll be at 0, because I have a half times 4 is 2, 2 minus 2 is 0, which means I'm going to be like this. So I'm going along, and this is what I'm filling. So I'm filling in a triangle here in the YZ plane. Now, that's just my two outer ones. I still have one more layer to go. Here we go. What's the last layer telling me? X goes between 0 and 1 minus a half y minus a fourth z. All right. Now, x equals 0, that's actually pretty easy. We actually have another name for x equals 0 in three-dimensional space. Do you remember what the name for x equals 0 is? It's the YZ plane. So x equals 0 is the YZ plane. Now, it probably is going to be useful. All right, so here is our direction x. It might be useful to understand this other surface. So x equals 1 minus a half y minus a fourth z is not so obvious what that is, but if we think about it this way, that's the same as saying 1 is equal to x plus a half y plus a fourth z. And now if we write it that way, it's a little bit more clear what that is. What kind of surface is it? It's plane. It's a flat plane. Now, you might say, well, how do we sketch a plane? And oftentimes, a good way to sketch a plane is to say, let's see where it hits the axes. So, where will I hit the y-axis? Well, to know where I hit the y-axis, you cover up the x and you cover up the z. When does x equal half y? At 2. So the plane is going to hit that point on the y-axis. Now let's go to the z-axis. So for the z-axis, I cover up x and y. So when does 1 equal a fourth times z? 4. You might say, wow, that's really convenient. Well, yes, as you're about to see in a second. Now, where do I hit the x-axis? Cover up the y and the z. So when does it, what? 1, yeah, at x equals 1. So I'm going to hit the x-axis here at 1. So that my plane, I can draw sort of a triangle of where it hits what's called the first octant, where x, y, and z are all greater than or equal to 0. Now, what's my shape? Well, remember, what is x doing? It starts at the back on the YZ plane at x equals 0. So it starts in the back, and then it moves forward until it hits this plane here. So what's our shape? Well, the shape is actually a very nice shape. What happens is I'm at 1, 2, and 4, and I'm forming a tetrahedron. So I'm forming this tetrahedron where I'm in the x, y, z are all greater than or equal to 0, and the front face of the tetrahedron is this plane. All right, so now that's step 1. We still have lots of steps to go, but we've got through step 1. Well, actually we got through step 2. We drew a picture. Good. And we were working up one dimension at a time. Ha. See, in some sense, we're like halfway there. Because it's like, now I understand what it looks like. Now we got to unravel it. Okay, so the unraveling. Well, we want to go in a particular order. So let's talk about the order we want to end up with. dz, dy, dx. So when I look at the order I want to end up with, I say, okay, dz, dy, dx, the last thing I'm going to figure out is the z, because I'm going to set the bounds from the outside in. So I'm going to start with the x, because that's on the outside, then the y, and then the z. So since I don't need to worry about z until the end, what I want to do is I want to look straight down the z-axis. So it's almost as if we're going to come here, we're going to grab a hold of that z-axis, and we're going to pull until we're looking straight down the z-axis. That's our goal. And if we can look straight down the z-axis, we'll see a picture. So I'm looking, so imagine I was an artist, and here's an eyeball, and here I am, I'm looking straight down the z-axis. So this is me looking straight down the z-axis. What do I see? I see a triangle in the xy plane. Because when I look straight down the axis is this single point here at the origin. And I'll see a triangle. Where does my triangle hit the x-axis? 1. Where do I hit the y-axis? 2. And so, in terms of the xy plane, my solid is sitting on top of this triangle. Now, I might say, oh, it's kind of like what we had here with the yz plane. And it is. See, we're going backwards now. All right. So we're making progress. So let's write our answer here. We're going to fill it in as we go here. Our function doesn't change. We don't even know what our function is. And we know the bounds dz, dy, dx. All right. So let's talk about x. Where does x go between? Again, outside bounds means I want to go between two numbers. Small number to high number. Where do I go? 0 to 1. Good. A third of the way done. Now, what happens? Well, we know x. So I say, imagine I'm at a particular x. And I want to say, where do I go for y? So I'm going to go from two curves. So I need to get a y equals for the bottom curve and a y equals from the top curve. So the bottom curve is this curve here. What does y equal there? That's right, y equals 0. Now it goes up to the slanted line. Now for that, we need to figure out the line. Well, it's not too hard because I know the intercept is 2. What's the slope? Negative 2, because I go down 2 over 1. So what's the line? Y equals negative 2x. Let's think of that as our mx plus b, so plus 2. Minus 2x plus 2. So where does y go from? It goes from that curve y equals 0 to y equals negative 2x plus 2. All right, so now I figured out my x and I figured out my y. What happens next? Well, go back to our 3D picture now. We no longer have to be looking straight down. So I'm going to pick a point here, x and y, and I'm going to go from the bottom surface up till I hit the face. Now the bottom surface is the xy plane. So the xy plane is the bottom. How do we write the xy plane in terms of z equals? Z equals 0. And now we have to figure out, how do you write this surface in terms of z equals? Well, there's my surface. And see, initially it was solved for x. Now what do? We solve for z. So let's solve for z. We'd get 1/4 z is equal to 1 minus x minus a half y. And then, we don't like the 1/4, so we get rid of it. Multiply everything by 4. Z is 4 minus 4x minus 2y. So that's the up surface, the top surface. And so, where does z go from? I go from z equals 0 is my bottom surface to z equals 4 minus 4x minus 2y. And we're done. That's it. That's it. And you probably will notice that the zeros are all the same, but the upstairs changed dramatically. So switching order of integration when you have interesting shapes is interesting. All right. Now, let's try another problem. So here, it's not a change in order of integration because there's no bounds given to us initially, But we're told the following. We have this solid shape. X, Y, and Z are all greater than or equal to 0, which means I'm sitting in my first octant where everything is non-negative. Y is at most 1. X plus Z is at most 1. And Z is less than or equal to 1 minus Y squared. Now, if we were just told that, we might have a hard time visualizing. But they gave us a picture because they're nice people. So when we see the picture, we can start to sort of visualize things. So this is the shape, some sort of weird doorstop-like shape. There's a few things we can spot pretty easily. So here, this bottom, what is that surface? So this is Z equals 0. I should try to mix up the colors here. What is this side here, this triangle? It's in the XZ plane, so that's Y equals 0. All right. In the back, here, I have this shape. What's this one? That's X equals 0. All right. That's 3 of my surfaces. Now let's see about the other 2. So I also have this front face. Now it's not so clear to me what that front face is, but if I look here in the XZ plane, I see this nice flat line. Notice X plus Z is equal to 1. Well, there's no Y dependence, which means really it's like I did something in the XZ plane and I copied it. So this front face here, that comes from the X plus Z equals 1 copied over. So I get X plus Z equals 1, which leaves us with just one more piece to go, which is this kind of cool looking ramp, which if you were very brave, you might ride that on a skateboard or a bicycle. Where does that surface come from? This is Z equals 1 minus Y squared. Because if you think about it, you can see it's sitting here in the YZ plane. And then it's like I'm copying that going forward. And so that comes from the last thing which we haven't talked about yet. All right. So now those are our pieces. And it says we want to integrate something over this shape. In particular, the goal is to say I want to integrate over my solid, which is spelled with a fancy D for some reason, 30 dV. All right. Well, we have choices. But some choices are easier than others. And for whatever reason, they have given us a hint that says, maybe don't do what we normally say. dx, dz, dy. Well, could we integrate dz, dy, dx? The answer is yes. But sometimes it's easier not to go with that method. You see, problems are easier in certain orders. We've seen this before where switching the order of integration takes a really hard problem and turns it into a mildly hard problem. And so it's good to be able to say, what's the right order? So our goal is to say, well, what should this be? So I want to integrate something to something, something to something, something to something. I don't know what they are yet. 30 dx, dz, dy. All right. So that's where we want to get to. Oh, boy. How to begin? How to begin? Well, the good news is we're kind of halfway through the process. Because what do we have? We have the bounds. They were given to us. We have the picture. And not only do we have the picture, we understand which pieces go where. What are the various surfaces involved? We've even labeled it as needed. So really, we're up to step 4 into what to do. All right. So let's make a little bit of progress. A little bit of progress is good. All right. So thinking about what we talked about just a few moments ago, what's the last dimension we're going to work with? the x dimension. That's the very last dimension that we're going to work with. So where should we look down? Look down the x-axis. And if you look down the x-axis, what will you see? Well, the good news is it's very easy to look down the x-axis because you're going to see the yz plane. And notice, you have the yz plane, drawn almost as if it was a set of axes. And what you'll see is this parabola shape. All right, so that's what we'll see if we look down the x-axis. Now this is not just any parabola. We actually even know what this parabola is. Z equals 1 minus y quantity squared. Do we know where it's going to hit the z-axis at? At 1. Do we know where it's going to hit the y-axis at? In other words, for what value of y do I get out z equals 0? 1. Okay, so here we go. We can actually put the bounds in pretty quick. So y goes from where to where? 0 to 1. Now that I have y, where does z go from? Goes from 0, z equals 0, to z equals 1 minus y squared. Now that I have y and z, well, where will x go from? Well, what's going to happen is I'm going to go from this back face to this front face. The back face is the x equals 0 plane. So I go from 0. The front face is this x plus z equals 1. So I need to get it in terms of x equals. So it goes to x equals 1 minus z. So that's the new bounds. There's a 30 there because we still need the 30. Now, we don't have time to finish this integral, but I'll tell you, this was from an old final exam, and this was number 7 on the final exam. And the reason I mentioned it was number 7 is if you carry out this integral, it does turn out to be 7. So, as good practice, just carry this integral out, and we'll do some more practice next time.